Okay.
Okay, great.
All right. So this is that's so, right?
Yeah.
Is this the right one?
Yeah, that's right.
Does it look good?
Just look. It's already on.
Okay.
So, okay, next speaker is going to be Ludwig Mathey. He will talk about scientific and quantum gravity.
Yeah. Almost. All right. I'm just going to use that. All right.
Yeah, first of all, I would like to thank the organizers very much for setting up this beautiful event in this very classy location. It's really a pleasure and an honor to be here. I would like to share with you some of our recent studies about time crystals in atom cavity systems. And I will first give some general remarks about the concept and the idea about time crystals, and then lead up to our platform that we are interested in, that we're working with here, which is this cavity BEC system that has also been introduced in 2 previous talks, and then share with you 3 of our time crystal states that we have predicted and observed in these systems: a discrete one, an incremental one, and a continuous one. From my side, so my PhD student, Jim Schulte, was involved in this and was really driving force and excellent student at this. And then my former postdoc, now sort of very much valued colleague, Jason Kostner, who's now professor in his home country in the Philippines. And of course, all of this done is in collaboration with the group of Andreas Hemmerich, collaboration that I value a lot, and his fantastic team with Hans Kessler, Håkan Buhl, Christoph Georges, Anton Julian, and former members as well. All right, so my pointer doesn't seem to work, so all right. Okay, so leading up to this idea and this notion of time crystals, of course, kind of this term was borrowed from regular crystals, which you are then, I guess, since this day forced to actually call spatial crystals, where sort of the key ingredient is that you imagine a system that has spatial invariance, for example, and which is then also realized in the ground state if you have some type of liquid system, and then sort of during crystallization you break the system spontaneously, sort of you reduce it to a type of lattice symmetry, sort of constituting this kind of phase transition of crystallization. Inspired by this, you can look at the time domain here, where you now have a Hamiltonian, which is time invariant, and you imagine now sort of, is there maybe some type of robust sort of steady state, equilibrium state that spontaneously breaks this time invariance here? And it would imply that you have some type of periodic motion that is indicated here. So that is at least one of the possible scenarios, so that has this direct analogy. We demand a little bit more of this here. We want this to be an analogy to a thermodynamic phase, in the same way that sort of the phase diagram of a regular material has kind of like a given sort of state, has a sort of extended space and parameter space. Therefore, having some type of robustness, we require the same of a time crystal, and also kind of robustness in general, in the same way that sort of the states of matter are still present, even if you have an imperfect realization, you have defects, you have boundary effects, and so on. So in general, kind of you can sort of demand something along the lines of that we are talking about a robust subharmonic many-body time limit cycle. That would be sort of, so we're using this as our working definition, and as you might have sort of heard, there are kind of a couple of different versions of what you want to call a time crystal and what you don't want to call a time crystal. It's a fancy word, sort of. I wouldn't mind sort of if we sort of replace it by this, but it's a little bit of a mouthful, and it's certainly easier to attract students if you call it time crystal. And sometimes I have to explain sort of, it's not actually time in itself that crystallizes, but it's something that sloshes back and forth in the system to sort of maybe reductionist view. All right, so the story of time crystals, so that it was phrased or like put forth by Frank Wilczek, proposing something along these lines. Here, sort of you imagine a closed system, and you imagine that you have a time invariant Hamiltonian, and sort of now, sort of the idea was, can we find some robust state which then in this kind of terminology would be now a continuous time crystal. It breaks this time translation and variance down to this kind of reduced kind of, in this kind of reduced fashion. It reduces it to a type of lattice symmetry as it is shown here. So closed system, time invariant Hamiltonian were the ingredients of this here. So shortly after, it was shown that sort of this proposal doesn't work. Sort of one criticism was in the specific example of that Frank used in here, and the other one was a more general type of logo theorem that sort of showed under fairly general conditions that sort of this scenario sort of cannot happen. All right, so but the word was out in the world, the inspiration was there. People try to sort of find other ways around it, so related scenarios that show maybe a similar sort of effect. All right, do you see this? Okay. So one direction was then, let's take a look at sort of Fouquet-driven systems, where we imagine that we have those systems which are periodically driven. Sort of now the Hamiltonian itself already breaks time translation symmetry. It's sort of reduced to a lattice symmetry. So you might ask sort of what is the remaining symmetry that is broken. Sort of one of them might be that now sort of this periodic motion here, the time period of the time crystal is, for example, a subharmonic. It's, for example, it's like an integer multiple of this periodic driving. That would be an example for a discrete time crystal. So that would be one scenario where you have a remaining sort of time symmetry gradient in the time domain. All right, so in this kind of scenario, closed systems for K-driven sort of led also to a first set of realizations. The group of Chris Monroe and ion traps, and also Misha Lukin in these centers in diamond like this one here. So my understanding of sort of interpretation of these experiments are that they are a type of pre-thermal time crystal. That's how they are discussed, my understanding. So I might be putting words in people's mouth, but this is my perception of it. Is that sort of these are sort of, if you keep going with your closed system that you drive periodically, and you here sort of certainly don't have any type of predictability or so, that these are sort of long-lived but not perfectly robust states. They are long time states, you will just overheat the system, leading due to Fouquet. Okay, so this led us then to this point. So what if we sort of introduce like a very weak sort of but well-controlled quantifiable dissipation in the system? Can we sort of take care of this Fouquet heating and generate sort of genuine sort of long-lived robust states? That was kind of the question that we sort of posed ourselves there. And this led us to this platform here designed by my colleague Andreas Herrlich, who also does a wonderful work talk about this from Tobias Dollar sort of and from the Estinger group. So basically the setup has already been introduced. Kind of we have a condensate in a high finesse cavity here, and one of these mirrors is assumed to be semi-transparent, so that you have your photon loss. That's our dissipation here. That's our dissipative channel with a sort of added benefit of giving you a time series, which is kind of very convenient if you look at time-dependent processes. All right, so here's our pump laser, and sort of in the following, we will either sort of pump the system with a constant pump intensity, or we will modulate the intensity, or we will modulate the phase of this retroreflected laser over here. So that's just coming up. Okay, so as already mentioned, so I can be, I guess, a bit brief on this here. So this system shows generically a superradiant phase transition. If you pump the system below a critical intensity, all you're doing is you just made a weak sort of optical lattice where you have now a periodic modulation along the transverse direction. Basically, the cavity mode is basically silent. It's just an innocent bystander of the system. Apologies. But then sort of beyond the sort of critical value here, the system becomes, the cavity becomes active, and the system organizes itself into this kind of checkerboard order, allowing for Bragg scattering out of the pump beam into the cavity mode, and then sort of starting to occupy the cavity mode, and now we start to see emission from the cavity here. Okay. All right, so this is what a typical data set might look like. You already saw this in Popper's talk earlier. So at earlier times here, we just have this kind of linear ramp here. All right, so I'm getting this. All right, so we have this kind of linear ramp here. And sort of, as long as you're below this critical value in this pump intensity here, the system has essentially no photons in the cavity, and the system and the atoms just are sort of in the condensate state, and you see these very weak kind of side peaks. That's from your optical lattice that you made. And then beyond this point, you see this on-side of the superradiant state, the photon mode is occupied, and you see simultaneously these kind of characteristic side peaks indicating this kind of Z2 symmetry breaking that emerges on this on the subcritical side. So I want to keep it light on the theory side. So I hope I don't want to ruin your lunch or so, but I want to element some of these sort of elements of our analysis we typically apply to these kind of different. For example, we can either sort of work in this kind of full many-body kind of representation of this, where you have the atomic field and the photon field. Then a very natural approximation is a few mode type approximation, because we already saw it on the previous slide, right? So if you have the condensate mode, you have the side peak, that feels like that we take those modes and approximate the full system by those specific modes. This gives you then kind of a few mode bosonic system. You can map this via some type of Schwinger boson mapping on variations of Dickey models, and also you can approximate this further via some type of Virchow-Klimakov type transformation. All right, and on the numerical side, we usually work with some type of open system truncated. Okay, let's stick a little bit with this Dickey model here. What are the two spins in our Dickey model? One of them is this momentum state here in the center, the K=0 mode, the condensate mode. That's our spin down, and the spin up is the in-phase superposition of these four states here. That's this kind of spin one half operator that is written here. Here's your photon mode, and you have some type of light-matter interaction coupling to this collective spin degree of freedom that is shown over here. And famously, this model has this kind of super radiant transition beyond this critical point in analogy to the transition that we saw in the cavity. You see what's on the y-axis here is the expectation value here in some type of mean field type kind of picture is the value of A, so meaning the electrical field that is generated in the steady state, and it can be positive or negative in the type of Ising type phase transition, showing you that the sign of this here is related to which of the two ordered state is realized. All right, so as a presentation device, I want, and then for you to play along at home, what I want to do is give for each of the time crystals a minimal model that you can type in Mathematica and sort of solve in like 20 minutes or so. I can send you my Mathematica file that I wrote for this talk, so if you want to play it out at home. Otherwise, you can just imagine you doing this, which is the art of being a professor. All right. Okay, so here's now our mean fields dynamics of this Dickey model. You have the three components of your collective spin over here. You have the A field, that's your photon field, and you have these are then coupled by this lambda here, which is for the light matter coupling, and we sort of here crucially included our sort of weak dissipative term here. All right, so and all of these parameters can be related to the parameters of the experiment. Here's the recoil energy, light shift, atom number. Here's a recoil energy giving you this effective kind of frequency here, and these are the definition of these parameters. So just go to Mathematica and solve like these coupled four differential equations, and sort of we can, for example, implement the sort of the example that I just showed you of taking this epsilon and just ramping this up linearly, and then this is the type of prediction that you get out of this here. So here you have this phase transition into the superradiant state. Here's the predicted photon number as a function of time, and this is, of course, supposed to remind you of the measurements that I showed you. Sort of, given the simplicity, we can amp this up, sort of over truncated Wigner, which is then more quantitative, but you're actually not too terribly far off, sort of, to showing you that at least gives you some idea about what's going on here. Okay, we want to drive the system now, and we want to do this in three different ways, as mentioned. We want to either sort of modulate the intensity of the pumping, or we want to modulate the phase, and finally we sort of wise up and just go back to the constant phase that we started out with, because the story that I told you about the phase transition isn't actually complete, as complete as I made it sound. All right, in any case, each of these types of modulation or types of driving gives you a different type of time crystal. If you modulate the intensity, you get a commensurate discrete time crystal with period doubling. In the case of the phase modulation, you generate an incremental time crystal. In this case, your Hamiltonian has a periodicity here. The time translation invariance is broken, but not in a commensurate way. We borrowed this word here just from incremental charge density waves in solid state, where you sort of have a periodicity. The periodicity of the density modulation of the electron density is not commensurate with the underlying lattice. That's what happens here. Sort of your time crystal period is not in any integer ratio, but it's actually a continuous function of the parameters that are accessible in this parameter. And then in the end, sort of I show you that sort of the slightly simplified story that I showed you is actually oversimplified, that there's actually a continuous time crystal in the original case of constant driving. Okay, so let's kind of start out with this intensity modulation. And I didn't foresee that this button is here. All right, so this is our protocol. We ramp up the intensity, keep it constant for a little bit, just because the experimentalists do that. That's actually a good idea. And then we start driving this here, and the periodicity is not rendered here. So basically, we are sort of modulating here the intensity. And let's see what our model gives you. So we're just solving these equations here. And we use this type of protocol now, and we can now take a look at what we find in this case. So here sort of everything starts out the way you saw it before. We go into the superradiant phase because we keep it constant, then the photon number is constant, and then the system sort of responds very strongly to it. There's a transient regime, and it sort of then has a periodic dynamics here. Let's zoom in a little bit to make this visible, and this is the type of dynamics that you see in here. So this is the modulation of the intensity in time. This is the photon number. You see that's essentially periodic. That's maybe a little bit on top of this, but it's essentially periodic motion here. Here you see kind of we drive sort of in the tens of kilohertz regime here. But if you resolve this, if you now look at the expectation value of A, the electrical field, you see that the sign of it changes back and forth in every second period, showing that you have a period doubling in the dynamics. I also want to give to Odin for this wonderful paper and for the subsequent work that discussed this scenario. Okay, so this is this kind of period doubling time crystal that we wanted to look at first, and we looked at the entire sort of dynamical phase diagram. And this is now the experimental realization of this. So here is the time axis. We have two time series here. The orange data is the photon number. The blue data is the relative phase between the pump beam and the emitted light. So basically here sort of it follows essentially the protocol that I showed you. Who knows why I picked this? Basically here, so if you go into the superradiant phase, and around here you start modulating the intensity, and you see that you get these bursts in the photon number here that are periodic with the driving periodicity. But if you look at the phase of the emitted light, you see that it switches back and forth between pi 0, pi 0, pi 0, giving you this kind of period doubling in this dynamics. And what happens on the atomic side is that you're switching back and forth between these two checkerboard orders from the odd to the even one in a single driving cycle, giving you this kind of period doubling dynamics in the atomic sector. Okay, so then let's take a look at our second example here. Now we want to modulate the phase of this drive here. So this would be an alternative way of driving the system in a periodic fashion. And now sort of we have to go back to the drawing board, because what I showed you before is a Dickey type model that includes these two momentum states, right? Those made up the spin 1/2 of our Dickey model. And now sort of, because of this phase modulation, we're activating a third state that has to be included, which is given over here. Now sort of we take a superposition of these four states, but these guys get a minus sign that would constitute some type of dark state. And if you write this down here, you end up with a 3-level system in a V configuration that is shown here, and sort of then it evolves, it expands into some type of 3-level Dickey model. So in this case now it's a 3-level thing, so apologies. So now you get sort of 8 sort of degree of freedoms. You're just using the freedom matrices. which describe the dynamics of this here. So if you have still sort of your A here, and then you have these 8 components here of your 3x3 matrix. And this would be the dynamics without the driving, and then it gets more complicated because here is now your phase protocol that enters here. Still, kind of, I would imagine one can type this into Mathematica, at least I did sort of on Monday, in case you're wondering. Sort of, if you, here's the protocol, sort of you ramp up the epsilon linear, keep it constant. Here's now the phase protocol. You keep it at 0 and then turn on the phase modulation over here. And this is what the photon number does. First, you ramp into the separated state, then you start modulating the phase, and you get some dynamics in this in the photon number over here. And let's zoom in here, sort of like here. So this is the type of dynamics that you then see in the photon number. This here is the phase protocols here, giving you an idea of the period of the modulation here. Now you see that the number of photons, now it's composed of 2 frequencies, right? There's a modulation that is commensurate with the phase modulation, but there's a much slower modulation like underneath it, right? There's another frequency. And actually kind of this underlying frequency is not commensurate with the driving periodicity, but sort of is actually continuous frequency depending on, for example, the driving frequency and so on, right? Okay, so if you can also look at the electrical field here, and you see that you get some sloshing between the 2 checkerboard states here. It goes from plus to minus, but sort of not at the driving frequency, but at this lower frequency over here. You can map out the dynamical phase diagram with truncated Wigner. Here, for your viewing pleasure, I brought a movie, sort of. So this, maybe let's focus on the upper, especially given the time. Sort of like this upper part here. This is like a small fraction of the lattice. The atoms here, we are in the superradiant state. The atoms have arranged themselves in one sublattice here. And now we're going to turn on the phase driving of the system. And sort of the way this then responds is you start seeing that it starts to get activated, it gets pushed back and forth here, and then sort of every once in a while now it kind of switched over to the other checkerboard state. So you see it has the driving frequency, but it also has this kind of slower sloshing dynamics underneath it that sort of is then periodic and constitutes this incommensurate time crystal of a driven state. Okay, all right, so this is then the experimental realization, sort of. I keep it a little bit brief. So again, so we have our photons in orange, and blue is the phase, and sort of we see that there are still these kind of bursts, and you see this kind of switching here between these the different between 0 and pi, sort of not commensurate with the drive, but sort of at a sort of emergent sort of frequency in the system here. Okay, so finally, we sort of, after chasing periodic driving around the block, sort of in the end we wised up and sort of just went back to the sacred texts of cavity BSC systems, just look at static driving. And specifically what we notice is that sort of in this phase diagram, there's actually like another regime, and actually there are several, sort of, as you also heard from Poplar on Monday, sort of, it's a okay, so specifically, so this kind of phase diagram should be extended to include continuous time crystals. So basically here, what we have to do is that we need to include sort of another momentum state over here, expanding this again to a type of 3-level Dicke model. In this case, it's this kind of 0-2 type momentum state. That's exactly the one that is activated in the optical lattice. So now kind of we again have a 3-level Dicke model. In this case, we can actually get away by integrating out this state here. And all that happens is that you go back to the 2-level Dicke model, but with a current nonlinearity of a certain magnitude that now shows up here in the equations of motion. So you can take the equations of motion that I showed you in the beginning, but add this kind of current nonlinearity, and let's see what happens then. Sort of in this case, we ramp up sort of the intensity, keep it constant, and the photon number here just oscillates with timing, right? So if you can here also zoom into this here and see that you have this periodic sort of motion of the photon number, even though you you pump with a constant intensity. The electric field does actually not slosh back and forth plus and minus. You're actually not sort of driving the system from one checkerboard to the other one. can also show this here to you in a movie. So let's focus maybe for brevity on this channel up here, on this panel up here. So this is again the real space depiction. We see the atomic density, we're in the superradiant state, and now sort of we now we sort of watch this kind of dynamics, and you see that in this case, the atomic density, you're actually sort of going sort of across the plaquette back to the symmetry broken state that that you started out with, right? You're kind of staying in the same sector, you're reducing the intensity quite a bit, and you sort of walk across this kind of plaquette there. All right, so this here sort of is a sort of another representation of this, and this was the experimental realization. Pop already sort of discussed this. All right, so it's she took the data, so it's okay. All right. Okay, so basically here what you see is you ramp into this into the state, and you see that the photon number has no business of being constant, but it really sloshes around in this periodic motion. You can check that this all is consistent with a given frequency. You can check that you spontaneously break the U1 symmetry. Here, this is an example for our open system truncated Wigner, where you also see this here. The timing is good, by the way. So it's like, and you can then sort of extend your phase diagram by showing these kind of limit cycle or continuous time crystalline regimes over here. Okay, so in conclusion, sort of, I showed you 3 scenarios of time crystals that we have realized over time. Sort of one of them is this kind of period doubling time crystal, which is achieved by modulating the intensity of the family. You can generate an incremental time crystal by sort of using phase modulation. And finally, sort of if you just go back to this constant driving, constant always in the sense of there's a rotating frame, and within the rotating frame you have a constant Hamiltonian, you can sort of generate a continuous time crystal. So this last case is actually the one that is closest to what Frank originally proposed, right? So like the only difference is you have like a weak dissipative channel sort of realizing this kind of proposed scenario. Okay, so I can't help myself but mention we also propose to generate time crystals in high DC superconductors. We sort of wrote like an open system truncated Wigner for lattice gauge theories. So basically here you drive your high DC, your 2 break, for example, from the transverse direction. You can map out the phase diagram and see that you have a Higgs time crystal here, which is induced at some resonance of the Johnson plasma frequency at the Higgs frequency. I'd be happy to chat about this. And just because it came up earlier, I'd also be happy to talk about our dynamical BKT transition in collaboration with a group of Chris Foote, where we sort of triggered this BKT by splitting the condensate, and you observe this kind of dynamical BKT transition captured by this real-time RG approach that we proposed some time ago. You can read about this, and I'd be delighted to chat about this here. All right, so in conclusion, this was the main message of my talk here, sort of that we I chatted a little bit about time crystals in general, sort of, and introduced the platform, and then sort of shared with you 3 of these time crystalline states. Let me here flash the papers that this talk is based on. Let me thank you so much for your attention.
So I have a question about this incremental. The incremental?
Yeah.
So in condensed matter, when we have an incremental charge density on top of a lattice and the pitch is very, very long, we basically consider it to be almost like breaking a continuous state. So my question is, what is the limits on this? It seems like you can sympathetically approach this no-go theorem. If you can make the ratio between the time very small.
Exactly. So, first of all, I think you're absolutely right that there's a breaking of continuous symmetry. So you could call that also a continuous time crystal. We just wanted to emphasize that we have a periodic Hamiltonian. The no-go theorem that I mentioned applies to a static Hamiltonian. So that's sort of outside of the scope of that theorem because we have a periodic time.
So in your animation, we saw how the atoms are moving from inside to outside periodically.
Yeah.
What's the speed of the atoms, and can you compare this to a critical velocity DC?
Yeah, so that's actually on a similar scale. So it's, I think it's actually, yeah, it is below the critical velocity. So it's interesting. Yeah, I see where you're I think it's below this one.
I think it was the amplitude drive, the intensity drive, where you said that you don't have like perfect periodicity, but kind of something that looks like periodicity.
Yes.
Would that qualify then as a quasi-crystal, like a quasi-crystal or not?
I love the question. Yes, like so on this plot, sort of it's a little bit along the lines of what I talked on Monday. So like if you keep going with this, you get like more bifurcations, you get root counts, and so on. And so in this example, maybe it's and file more pointers, so where you're already sort of almost like going to the next kind of bifurcation. So it's nothing between higher frequencies, higher harmonics. So I think the predominant it's still kind of closest to the theory, but in theory, it's not really using a higher